In this video, we're going to continue our study of area and the fundamental theorems of calculus and really sort of dive into how we use definite integrals to find area. We'll also look at some of the properties around definite integrals. First, a quick review. Remember that the first fundamental theorem of calculus states that the derivative of the integral from a to x, where a is just some constant, of f of t dt is equal to f of x. And that implies that this integral right here, this definite integral, is an antiderivative of f of x. And so if we let capital F of x equal that antiderivative, then when we take the quantity f of b minus f of a, that gives us the definite integral over here. And so we looked at this in an earlier video, and if you want to see the details of that, then go back and look at that earlier video. But really, this is what we call the second fundamental theorem of calculus. The second fundamental theorem of calculus says that the integral from a to b, a and b are just constants, of some function here with respect to x is equal to f of b, capital F of b, minus capital F of a, where capital F of x is an antiderivative of little f of x. And so this gives us our way of finding area underneath a curve. So let's look at an example of this. All right, we want to start off by just finding the area of the shaded region here. Our function is y equals cosine of x. We can see that what we've got here is we've got a shaded region here. Now we know, just because we know about cosine, we know some properties here. We know that that this value right here, where cosine is equal to 0, is negative pi over 2. And we know that this value right here is positive pi over 2. You could also sort of see that because, here's 0, here's pi, and that value's right there in between them. And so we know that that's negative pi over 2 to positive pi over 2. And we need those values because those are going to be your upper and lower limits for this definite integral. So we know that the area that we're looking for is equal to the definite integral from negative pi over 2 to positive pi over 2. Our function that we're looking at here, we want the area underneath the curve of cosine of x. So we're doing cosine of x here, and we're doing this with respect to x. Okay, so how do we do this? Well, let's see. I need an antiderivative of cosine. So what is it that we take the derivative of to get cosine? We know that that would just be sine of x. So an antiderivative is sine of x. And we're going to use our notation here. This long line with pi over 2 at the top, negative pi over 2 at the bottom, just means that I need to stick pi over 2 into here, I need to stick negative pi over 2 into here, and I need to do the appropriate subtraction there. And so what I get is I get sine pi over 2 minus sine negative pi over 2. Which gives me, let's see, sine pi over 2 is equal to 1 minus sine negative pi over 2 is equal to negative 1. And so it looks like the area that we're looking for here is equal to 2. This shaded region has an area of 2. All right, and so that's how we did that. We used the second fundamental theorem of calculus to find an antiderivative, plug in the upper and lower limits, and we got it. All right, so let's just do another example here. We want to find the area of the shaded region. And in this case, we've got this function y equals 1 over x squared. It looks like we're trying to find the area between 1 and 2. And so that area would be, let's see, that would be the definite integral from 1 to 2. Our function here is 1 over x squared. I'm going to go ahead and write that as x to the negative 2. We know that's the same thing. Okay, so that definite integral right there, if we can find that value of this, then we should be able to find the area. So let's see. I need to find an antiderivative here. And so I know an antiderivative of x to the negative 2. Let's see. I add 1 to the exponent, I get the same number downstairs. So that would give me an x to the negative 1 over negative 1. Let's just go ahead and rewrite that as negative 1 over x. And now I need to evaluate that from 2 down to 1. Okay, So I'm going to plug in 2 in place of x. So it looks like I get a negative 1/2 minus, and then I need to plug in 1 into x. So I get a negative 1/1. And just cleaning things up here a little bit, looks like that would give me negative 1/2 plus 1. Looks like the area of the shaded region right here would be 1/2. All right, so let's look at another example. Okay, I want to evaluate this integral right here. I want to evaluate the integral from 1 to 2. I've got 6z squared minus 3z. I'm integrating with respect to z. So remember, it doesn't have to be x's here. This is really just a dummy variable. Anyway, it doesn't really matter what it is. But okay, I'm going to go ahead and see if I can find this. All right, so I'm going from 1 to 2. I've got 6z squared minus 3z dz. Okay. Let's see here. Let's go ahead and find an antiderivative. Looks like here I would get 6z cubed over 3. Remember, we're going to add 1 to the exponent and get the same number downstairs. So 6z cubed over 3 minus 3. Looks like this is going to be a z squared over 2. Okay, that's my antiderivative. I'm going to go ahead and clean that up a little bit here. I'm going to rewrite that as, let's see, the 6 over 3 just cancels. Looks like I get 2z cubed minus 3/2 z squared. That's my antiderivative. And I know that what I need to do here is I need to evaluate that from 2 down to 1. Okay, so that means I need to stick a 2 in there wherever I see a z. I need to stick a 1 in there everywhere I see the z, and then subtract those two quantities. And so let's see, what do we get? We're going to get, let's see, let's put the 2 in there. So we're going to get 2 times 2 cubed minus 3/2 times 2 squared minus. And now here's the place where you really want to watch out. We're about to subtract off. We're about to plug 1 into here, and we want to subtract whatever we get there from this quantity right here. So when you do this, make sure you put parentheses right here. We're about to plug the 1 in there, and whatever this turns out to be, we're subtracting all of that. So we get 2 times 1 cubed minus 3/2 times 1 squared. Okay. And just cleaning all that up, let's see, that would be 2 times 2 cubed. 2 cubed is 8, so that's going to be 16. Minus 3/2 of 2 squared. So it looks like, one of these 2's would cancel with this one, so that would give me a 6. So it looks like this part here is going to be 16 minus 6. That's this first grouping right here. Minus, let's see what this turns out to be. Looks like this is just going to be 2 minus 3/2. So, okay, there we go. So what do we get? Looks like 16 minus 6 is just 10. 2 minus 3/2 is going to be 1/2. And so it looks like I end up with something like 19/2. If I write 10 as 20 over 2, then I can just do the subtraction. 19/2 is what I get right here. Okay, so let's do another example. Here we want to evaluate from negative 27 to positive 27, x to the 1/3 dx. All right. Let's just go ahead and rewrite this. Let's see. Well, I'll write the original integral. X to the 1/3 dx. Okay. Now I'm going to rewrite this here. No, I'm just going to go ahead and just do this. I'm just going to go ahead and just evaluate it. Let's see. So we need an antiderivative. So I'm going to add 1 to the exponent. So I've got 1/3 right here. Let's see. That would be x to the 4/3 over 4/3. That's my antiderivative. And I'm going to rewrite this. I'm going to go ahead and clean this up a little bit here. So let's see. That's the same thing as if I multiply the top and bottom of this big fraction by 3, then I would get a 3x to the 4/3 over 4. Okay, and don't forget we got to do this from 27 down to negative 27. I'm not writing that. I probably should, but I know I'm going to put that in here in just a minute. And I'm actually going to go ahead and take this one step further. I'm going to go ahead and rewrite this as 3/4. Let's see. This would be the cube root of x to the 4th, because that's what that's x to the 4/3. That's the cube root of x to the 4th. I could put the 4th here, or I could put the 4th in there. It's the same thing either way. And this is what I need to evaluate from 27 down to negative 27. Okay. So let's go ahead and see what we get here. We get 3/4 times the cube root of 27 raised to the 4th. Okay, that was putting 27 in there. Minus 3/4 times the cube root of negative 27 raised to the 4th. Okay, fine. Which ends up giving me, let's see, the cube root of 27 is 3. So I've got 3/4 of 3 raised to the 4th. All right, so 3/4 of 3 to the 4th. All right. And the cube root of negative 27 is negative 3. So I've got minus 3/4 of negative 3 raised to the 4th. Okay. And I could go ahead and evaluate this. 3 to the 4th is 81. Negative 3 to the 4th is also 81. But I think you can see here that this quantity is the same as this quantity over here. Right? That negative doesn't really do anything because it's raised to the 4th power, so it's actually positive. And so I've got something here minus pretty much the same thing. Looks like this ends up giving me 0. And some of you may be saying to yourself, hey, self, why did I get 0 here? I thought that I was finding area of something. And the definite integral is the area in some circumstances, but it's actually a lot more general than that. And so if we go in here and take a look at what this graph looks like, then I'm going to show you kind of why we end up getting 0 here. So I could do this in a calculator, or I'm just going to draw it right here. The cube root of x, okay, which is what x to the 1/3 is, that's just the cube root of x, looks something like this. Okay? And so I've got negative 27 over here somewhere, and I've got positive 27 over here somewhere. And it turns out, and we're going to see this here on the next page, it turns out that if we are finding area underneath a positive curve, like if we were looking at this part over here, if we were finding just that area right there, that integral from 0 to 27, that would have given us that area right there. But if I did the integral from negative 27 over to here, what I'm actually getting is I'm actually getting the opposite of area. And so when I integrate from negative 27 to positive 27, what's actually happening is that those things are canceling each other out. And so really what the definite integral is doing is it's kind of like a balancing function here. It's if you're integrating over an interval down here, and if some of the time that function is below the x-axis and some of the time that function's above the x-axis, then if there's more area above the x-axis than there is below it, then you're going to get a positive number. If there's more area below the x-axis than there is above it, you're going to get a negative number. And if you have something like this in this case, where you have the same amount both above and below the x-axis, then they cancel out and they end up giving you 0. So, okay, that's really what the definite integral is doing. And we've got to remember that, because what that means is that every time I do a definite integral, I'm not necessarily finding area. I am if the function is always above the x-axis. But if sometimes it's above and sometimes it's below, then what I'm actually doing is I'm sort of canceling out the positive part with the negative part. Okay, so that's one of the things that we have to keep in mind here. And so I think it's probably a pretty good time to just kind of think about some different properties of definite integrals then. All right, so if we have a function here that is greater than or equal to 0 over some interval, a to b, then this definite integral right here is giving us the area between f of x and the x-axis over AB. And if I wanted to draw just like a quick little picture here of that, here's a function above the x-axis, here's A, here's B, and what we're finding right there is we're finding area, and fine, no problem, that's what we got. If f of x is less than or equal to 0 over AB, then the definite integral is the negative of the area between f of x and the x-axis. All right, so in this case, what I'd be finding is I've got some kind of a function here that's below the x-axis. Here's my f of x. All right, and here's a to b. And so you're finding the area below it right here. This is an area. This isn't the area of this region. It's the negative of that area because it's below the x-axis. And so we got to remember that. And if f of x is both above and below the x-axis over that interval, then this is the difference of the area above the x-axis and the area below the x-axis. Okay? So if sometimes it's above and sometimes it's below, then what we're doing is we're taking that positive part and we're subtracting off that negative part, and you know, they're just kind of canceling each other out. All right, so let's look at some other properties here since we're talking about these things. The integral from a to a of any function is equal to 0 for any value of a. And that's really because all we're doing here is, you know, you got some function, and if we're going from a to a, there is no area. You have to have an actual region here for us to find area, and this is just a line. And so that's going to be equal to 0. That's pretty straightforward. Here's one that's not quite so easy to see. But what this allows us to do is it allows us to switch the values of a and b, and if we do that, we're introducing a negative. Okay, so sometimes we're doing different types of things, and sometimes we just need to switch those limits for different reasons. Okay, fine, we can do it, but what that means is that we're actually introducing a negative to this. Here's another property. Let's say that we've got some inequality here. A is less than or equal to b, which is less than or equal to c. And if I find the definite integral from a to c for this function, that's equal to the integral from a to b plus the integral from b to c. And that's pretty straightforward, pretty easy to see actually. I know that a is less than or equal to b, which is less than or equal to c. Okay. And I'm just going to do this for a function that's above the x-axis, but it really also applies, you know, whether it's above or below or both. But you know, if I'm going from a to c, then what I'm doing here is I'm looking at this entire area over here. I'm looking for the region, the area of this entire region right here. That would be this definite integral right here. But I could break that up into two different ones because I know that that entire area right there would just be the area of this one, which is the integral from a to b, plus the area of this one, which would be the integral from b to c. And so that's a pretty straightforward property as well. And here's another one that is sometimes a little bit useful. It's sometimes this is a time saver type of property. If f of x is an odd function, that is, it has symmetry through the origin, then if I'm going from negative a to positive a of f of x, that equals 0. And remember, an odd function is one that has origin or symmetry through the origin, something like this. And so if I've got some value a, and I go over here to negative a, then we can see that that would just cancel out because we have the same amount of area above and below the x-axis. And so that's just going to equal 0. And that's exactly what happened here in this previous example. X to the 1/3 was an odd function, and so negative 27 to positive 27 just ended up being 0. We could see the actual details here, but you know, we could have just used a property that says, hey, if I recognize x to the 1/3 as being an odd function, then negative 27 to positive 27, oh, that's just going to equal 0. And so sometimes that's a time saver. And I'll just remind you that a function f of x is odd you probably remember this from pre-calculus, but f of x is odd if f of negative x is equal to negative f of x. And so there's lots of different functions like this. X cubed, x to the fifth, x to the 1/3, sine of x, tangent of x, all of those things are odd functions. You know, there's lots of other ones, 1 over x. And so if it fulfills this, it's an odd function, and we can find these kind of integrals pretty easily. Okay, so let's get into another example here, and we're not going to actually do any integral here. What we want to do in this case is actually just write an expression that represents the shaded area here. Okay, so our function is the absolute value of x minus 2, and we want to write an expression that represents the shaded area here. Okay, all right. So we want the area here. Should be pretty straightforward. I should be able to find this one right here, pretty easily. The area over here is going to be, let's see, that goes from -6 to -2. All right, so absolute value of x minus 2. Don't forget your dx. That's part of your notation. And I know I just write that down because this was above the x-axis. I think you can see I can do the same thing for this part over here, which I'll put that. That's going to be my third one over here. What about this one right here? If I write the integral from -2 to +2 of this function, then that's not going to give me the area right here. That's going to give me the opposite of the area. That's going to give me the negative of the area. That's going to be a negative number right there. And so, if I want the actual area of this entire shaded region, I need to subtract that because that's the opposite of what it is that I want. So -2 to +2, this one right here, because this is below the x-axis. Okay. And then this other one over here, well, hey, no problems for this because that's above the x-axis. That would just be the integral that goes from 2 to 4 of this function. And we got it. So watch out. If what you are asked for is area, you got to check and make sure that that your function, you got to make sure you know where the function's above the x-axis and where it's below the x-axis. If it's always above, then you just write down the definite integral and you solve it and you got it. If it's always below, well, that's also kind of easy too. You just write down the definite integral, get that answer. That's going to be a negative number. Just take the opposite of that. But if it's sometimes above and sometimes below, then what you got to do is break that up into each of those different regions. You have a different integral for each one of those. And the one that's below the x-axis, remember, that's going to give you a negative number. And so you got to subtract that. You're subtracting a negative, which means you're actually adding that area. Okay, maybe a couple more little examples. These will be pretty straightforward, pretty quick, I think. Suppose that we know that the integral from 1 to 20 of 1 plus cosine of ln of x dx is equal to 10.6. The integral from 1 to 60 of 1 plus cosine ln of x dx equals 16.67. I want to find the value of the integral from 20 to 60 of this thing right here. All right, now I have purposely put in sort of a really nasty, ugly looking function. 1 plus cosine ln of x. We don't have any kind of rules or integration properties or anything that tells us how to evaluate that. But I don't need to. It doesn't really matter what this function is right here. I'm going to use properties of definite integrals to do this. And in fact, I'll tell you what, I'm not even going to write 1 plus cosine ln of x. I'm just going to write f of x and know that that's what that represents. What I've got here is I am told that, let's see here. I'm told I've got some kind of a function. And I'm writing this as, I have no idea what 1 plus cosine ln of x looks like. I'm just writing it down as some kind of a function right here. What I know is that if I go from 1 to 60, I know what that is. I know that's 16.67. All right, so from here all the way over to here, I know that's 16.67. I also know that if I go from 1 to 20, then I know that's 10.06. So I know this entire area, and I know this one over here, and what I'm asked to find is this one over here. Well, it should be pretty straightforward that if I know the whole thing, and I know this one right here, then really all I got to do is just sort of subtract the smaller area from the larger area, and that'll give me this one over here. I can write that down a little bit more formally as, using my property. I know that if I go from 1 to 20 of f of x, and I add that from 20 to 60 of f of x, then remember we have a property here that tells us it is this property right here, that if I know that a is less than or equal to b, less than or equal to c, then I can rewrite this integral right here. Then I know that that is equal to the integral from 1 to 60 of f of x. And now I'm just going to fill in what I know. The integral from 1 to 20 is 10.06. This one, I don't know. I mean, this is the one I'm asked to find, so I'm just going to kind of leave it in there as it is. On the right-hand side, I know that this is 16.67. That was told to me. And so if I just, subtract, it looks like what I can say here is that the integral from 20 to 60 of f of x dx is equal to 16.67 minus 10.06. Looks like that's going to end up giving me 6.61. All right. So really, I wasn't evaluating any definite integrals up here in terms of the function. I'm really just using the properties of definite integrals, and sometimes that's kind of how we do these things. How about we look at one more example, and I want to evaluate here. I want to evaluate this function. Okay, so I've got the integral from negative pi to pi of x plus sine of x minus x cubed plus 1. Okay, and I'm doing that with respect to x. Okay, now I could go in here. I know how to find the antiderivative of x, right? That's x squared over 2. I know how to find the antiderivative of sine of x. That would be negative cosine of x. I know how to find the antiderivative of x cubed. That would be x to the 4th over 4. And I know how to find the antiderivative of 1. That would just be x. But if I'm a little bit more careful here, I could recognize that x, sine of x, and x cubed are all odd functions. If you think about the graphs of those things, they all have symmetry with respect to the origin. X is just a line that goes through the origin. Sine of x, it's that periodic one, but it goes through the origin. X cubed is sort of comes down and over and down, and that's got symmetry through the origin. Those are all odd functions. And so if I use my property that says that if f of x is an odd function, and I'm integrating from negative a to a, that just ends up being 0. Now you got to make sure it's going from negative a to a. If this was going from 2 to 5 or anything like that, this doesn't help you. You'd have to go in and actually do the integral. But in this case, I've got negative pi to pi, and so I know that when I integrate here, that's going to give me 0. That's going to give me 0. That's going to give me 0. That's not. 1 is not an odd function. But I know that if all these other ones end up being 0, then really what I've got is I've just got to evaluate from negative pi to pi 1. And what is an antiderivative of 1? Well, it's just going to be x. So stick the pi in, you get pi, minus. Stick the negative pi in, you get negative pi. Looks like what we end up with here is 2 pi. And that was a lot easier than actually going and doing the antiderivative of all those things. So, it's worthwhile to make sure you kind of, go back and review what it means to be an odd function, and make sure you can recognize those things. And when you see these kind of integrals that go from the negative of a value to the positive of that value, and make sure it's the same value, make sure those are exact opposites. But if that's the case, you can just forget about the odd parts here, and go ahead and just find the integral of whatever's left. Okay, everybody, I hope that's helpful. Best of luck to you.